Students, so let's see now how you get Kepler's laws from Newton's laws. Kepler's laws are phenomenological. Kepler was interested in how the planets move. Newton's laws, though, are first principles. So Newton explains the causes of the motion. So let's see how we can do that step and explain Kepler's laws from Newton's universal gravity and the laws of motion, which was actually a point of validation for Newton's theory. So let us consider Newton's second law, that the force is the second derivative of the position. And consider then the motion of a planet. The acceleration are two dots. The acceleration is gravity, and sun here is the mass of the sun. So let us consider the radial position vector, and its derivative is r dot is equal to r dot r hat plus r hat dot. Now, the radial and the azimuthal unit vectors are a rotation of the Cartesian unit vectors, with the rotation matrix being, so the unit vectors are r hat is equal to cosine phi x plus sine phi y, and phi hat is equal to minus psi phi x plus cosine phi y. So we want to know r hat dot, the derivative of r hat. The unit vectors x hat and y hat are fixed in space, so they do not change. But the angle phi is a function of time. Thus, you take the derivative of this equation, and that becomes r hat dot is equal to minus psi phi dot x hat plus cosine phi dot y. And in this parenthesis here is phi hat. Thus, r hat dot is equal to theta dot theta hat. So if you substitute this onto the equation for the velocity, now for the acceleration, we simply need to take the derivative of this equation. So applying the chain rule here, we have, I know all the terms except for phi hat dot, that we need to take the derivative of phi hat, which is minus cosine phi dot x minus sine phi dot y. And in parentheses here, you have r hat. So phi hat dot is equal to minus phi dot r hat. Substituting that into the acceleration, so there are two expressions, one for the radial acceleration and one for the azimuthal acceleration. Now we compare this expression with the force of gravity. This becomes the radial acceleration is equal to gravity, and the azimuthal acceleration must cancel. So let us examine the second equation first. So this equation here is of the form AB dot plus A dot B, which means that it can be written as a time derivative of AB. Indeed, if you multiply this by R, this is the product rule of R squared times phi dot. So this quantity, let's call it big L, is the modulus of the angular momentum. So this equation implies that the magnitude of the angular momentum vector is conserved. Notice that with this, you can immediately prove Kepler's second law. If you are in orbit and you move in an infinitesimal time interval dt, then you're moving in the orbit by an infinitesimal angle d phi, and the distance that was traveled is r d phi. So the area that is swept by the vector radius is r d phi times the base of this triangle, which is r over 2. Now if you divide this by dt, so this is r squared phi dot, write this in dot notation, and this is the angular momentum. If you take again a derivative, due to conservation of momentum, this must be equal to 0. So that means that A dot is a constant. It means a planet sweeps equal areas in equal times, proving for dynamics Kepler's second law.